Okay, so yes, any questions before we start? If you remember, we started studying the magnetic induction on Wednesday, and today we will continue. We were basically studying the magnetic force. So we had written down the Lorentz force. We know that if we have a charge moving in a region of space where there are electric and magnetic induction fields, the force acting on it is given by this form, which if you exert it, apply it to a current carrying wire, then the force would be just I times dl cross B. This is your wire. If there is a magnetic field in this region, you just take a small segment. This is the direction of the current. Let this vector be dl. This is the force acting on that very small segment. Now, any questions?
Hocam şu en son yazdığımız bir kuvvet şey var böyle işte vektörel çizdik. Ona böyle etkileyen.
Now that we will continue. One of the things that we were trying to understand is that if this is the force law, the work done by a magnetic induction by this B field would be that just the force due to that B field multiplied by dl under a very small displacement, which is Q times V cross B dot dl, which we can also write if the object moves this distance dl in a time dt, that basically means that its velocity is dl over dt cross B dot dl. But dl cross B is perpendicular to dl. So if you just take the scalar product of two vectors that are perpendicular to each other, this scalar product is just 0. So on one hand, this tells us that the magnetic field doesn't do any work. But on the other hand, we had this example where we have this uniform magnetic field parallel to the ground, or perpendicular to G. We attach a circuit such that half of the circuit is in the region of magnetic field, the other one part is out of the magnetic field, and we hang a weight and send a current through this circuit. And we said that if I is equal to I0, where I0 was equal to, let's say this is the height h, mg over IHB, now mg over HB, sorry. If the current is equal to this value, then the net force acting on our circuit is 0, so it just hangs in the air. The magnetic force balances the gravitational force, and hence the net force acting on the mass would be 0. But if I is larger than I0, then the upward force due to this magnetic induction is larger than the weight in magnitude, but they are pointing in opposite direction, so our system moves upward. Well, it is accelerating. There is a force upward. It is being displaced in the upward direction. So there is work done on our system. On one hand, we said that magnetic field doesn't do any work. Now here it seems that the magnetic field is doing work. So that was what we were trying to understand, and that is where we will continue from. Any other questions?
Şimdi magnetik iş yapıyor mu, yapmıyor?
So you see, look at this derivation. The magnetic force doesn't do any work. Point. Magnetic force doesn't do any work. Okay, that is the final remark. But, okay, these buts are always dangerous. Is look at this problem. If it is not the magnetic field that is if it's not the magnetic field doing the work, something is doing the work. So what is doing the work?
Battery.
The battery will be doing the work. So that is what we will study now. So how much work does the battery? How is that connected with the you see the battery? We need the battery to run this current. And we actually said that, let's say at a given instant, the wire is moving upward with a velocity, let's say u. The charges are moving along the wire with a velocity v in the rest frame of the wire. There is the vertical motion of the wire. Let's say it's moving with velocity u. The total force, total velocity of the charges in the wire are this one. And we said that, okay, if this is the case, then this is the magnetic force acting on the charge. Now, this magnetic force has a component, both a parallel component and a vertical component. Parallel to the wire, but it is in the opposite direction to the motion of the charges. Actually, when we are talking about currents running in the metals, the charges are negatively charged. And furthermore, they are moving in the opposite direction. But for the conventionally, the current is defined to be the direction of the positive charges. And we will most of the time talk about positive charges moving in the direction of the current. So that's also what I'm actually doing over here. You can just repeat the same process for negative charges. So everything will, the force, if you would say that, okay, there are the negative charges, the velocity will be pointing in this direction, u is upward, this will be the velocity, this will be the force, there will be a vertical component which will be the same, the horizontal component which will be again in the opposite direction to the motion of the charge. It doesn't really make any difference, but just for the sake of simplicity and consistency, let's say, we are talking about positive charges being moving. So we have positive charges moving in this direction. There is this component of the magnetic force in the opposite direction. So unless there is a battery, for example, that is pushing our charges, the current will not be able to run through my system if the wire is moving vertically upward. So the battery has to do work. Now the question is, how much work does the battery do? To calculate the amount of work that the battery does, we have to calculate the perpendicular and the parallel components of this force. Let's first look at them. Now, on one hand, we know that the total magnetic force, the magnitude, is nothing but q v prime b. Well, v prime and b is into the screen. V prime is on the screen. So v prime and b, they are perpendicular vectors, so we don't have the signs or anything else. So this is the magnitude of the force acting on this charge. Now, the perpendicular component, let's call this angle theta. This angle will also be theta. The perpendicular component of the force will be just Fb times cosine theta, or Fb times Q times v prime times cosine theta times b. But you see, v prime times cosine theta is nothing but v. So the perpendicular component of the force will be qvb. The parallel component, on the other hand, this is fb times sine theta, which will be qv prime sine theta times b, or the parallel component will be qub. This is the force acting on a single charge. Well, let's say the charges along this length, there are lambda of them. Okay, let's also make one more distinction. If you just pick up a wire, this wire is neutral. Although there is a current running through it, the wire is neutral. So the lambda linear charge density of the wire is 0. But I can separate this linear charge density into, there are positive charges that are at rest, plus negative charges that are moving in this wire. So I can just look at the negative charges and say lambda to be the charge density of the moving charges. So this lambda over here, is not the total linear charge density, but it's the charge density of the moving charge carriers. So with that in mind, so the total perpendicular force will be just lambda times h. This is the total amount of charges that are moving. Each one will feel a force given by that expression QVB times QVB, which is lambda times V times Q times B times H. No, sorry. Lambda is the number density of moving charges. It's not the charge density, but the number density. Because the charge we had already, each one of them has this much charge. So I have lambda h of them, the length is h. I have lambda of them per unit length. So in total I have lambda h of them, q is the total charge. I can just rewrite this in this form, lambda times V times Q. This time lambda is the number density, Q is the charge of each one. So lambda times Q is the total charge density. Multiplied by the speed, that is nothing but my current. This is equal to I times V times H. Well, this is what we said the force was, and we just obtained the same force starting from the force acting on a point charge. Now let's look at the horizontal component. Now the horizontal component will be lambda times h. This is the total number of charges in my wire. Each one is feeling a force QUB. So this will be equal to lambda q times u hb. So this should be the force that the battery is kind of creating. Now let's look at the time dt. The charges move a distance v times dt along the wire, parallel to the wire. So the work done is F parallel total times v dt. This should be the work done by the battery, which is lambda q u v h b dt. Well, again, lambda times q times v h b u dt. Well, lambda q times v is nothing but the current running through my wire, I times h times b. U dt, remember u is the vertical velocity of the wire. So u dt, vertical speed times the time, is nothing but the displacement times dl. You see what we started with. dW is the work done by the battery, which we say that, okay, it has to counteract this horizontal force. The magnetic field is creating a force in the backward direction. So the battery should provide a force that is pushing the charges. So it should exert the same amount of force in the opposite direction. Along the wire, it will push the charges. In a time dt, the charges are moving with a velocity v. In a time dt, they will move v dt, this much distance. So the work done is the force multiplied by the distance. Now, if we just reorganize the parameters, this is what we get. Here we have the lambda q v. V is, again, remember, the horizontal speed. This is the current. H times B is already there. That's part of the force expression over here. And then we have what is left is U times dt, where U is the vertical speed. Vertical speed multiplied by the distance just gives me the vertical displacement. So the work done by battery is equal to this expression. But this is nothing but the work done by the vertical force. This is the vertical force. This is the vertical displacement. So the work done by battery is actually the vertical displacement we have. So this is kind of showing that the work done by battery is equal to the work done by this vertical force we have. They should be equal. But now there's still the question, how does the magnetic field do this thing? How does it convert the work done by the battery to the work done by this vertical force? Let's look at it in a bit more detail. Okay, this is exact equality between the forces. Let's look at it qualitatively. So what is actually going on? Here is our wire. There is a current running through it. So I have this charge which is moving in this direction. The magnetic field is into the screen. The magnetic induction field. Again, I'm just assuming these charges are positive. What will be the direction of the force acting on this charge? The force. Remember, the force, magnetic force, is Q times V cross B. This is V. B is into the screen, this is V, this is B. V cross B, the force is upward. So it will basically start doing a circular motion. Now it will hit the end of at least some of the charges will just hit the end of the wire, the surface of the wire. But you see, the wire basically acts like a kind of a potential wall, potential valve. So the charges are free to move inside, but they cannot go out. So when they hit the boundary, the wire will will pull them back into the wire. It will not allow it to go out. It's like a potential valve. You are free inside, but you cannot go out. So that means when it comes here, it will hit this wall. You can just basically think of it as a wall. When you hit that wall, you will bounce back. So when you hit this wall, the wall exerts a force on you, pushing you back. But now remember Newton. If the wall exerts a force on this charge, then this charge is exerting a force on the wall. So if you put a magnetic field, well, the charge is being accelerated in this direction due to an electric field in this direction. This is the direction of the electric field inside our wire. So the electric field is accelerating these charges. They are gaining velocity due to the electric field. Then the magnetic field just rotates this velocity vector towards the wall, and when they hit the wall, they will exert a force. And then they will bounce back. The magnetic field will curve them, and the electric field will accelerate them, and they will hit it again, exerting another force.
Elektron yani böyle hareket ederken tam manyetik force çıkar ama bu şekilde giderken onun her an velocity değişmiyor mu?
Of course. So at this point, it will have a force in this direction.
O zaman manyetik kuvvetin de her an değişmesi gerekiyor.
It is changing. You see, at this instant, it is in this direction. At this instant, it will be in that direction. It is rotating. So we will study this motion now. So we will see that actually makes a circular motion. But if the radius of the circle is larger than the size of the wire, or larger than this distance, its distance from the surface, it will hit the wall. It will hit the surface. So what is the work that the magnetic field does on this charge? Zero. Magnetic field doesn't do any work. It is the electric field over here that is doing the work on the charge, that is accelerating this charge, that is causing it to have a velocity. Once it gains velocity, the magnetic field just rotates it so that it hits the surface of the wire. And once it hits the surface, these charges exert a force on the wire because the wire is exerting a force on them. So again, magnetic field doesn't do any work, but it kind of rotates the direction of the force that is doing the work. It is actually this electric field that is doing work, which causes the wire to be pushed upward. Now, there are two examples that we will discuss. One is the simpler one. What will be the motion of a charged object in the absence of an electric field? That is what we will discuss first. And then on top of this problem, we will add the electric field. So basically, it's this motion. What is the trajectory of these charges? Of course, assuming there is no resistance. Now, any questions up to this point? Could I convince you that the magnetic field is not the one that is doing the work?
Yeah. In the formula, for example, lambda QU HB, which is total force.
The parallel component of the total force.
Yes. What is H? H is length of the
H is the length of the wire.
And lambda H is Q. Can we say that it's
Lambda H is not equal to Q. Q is the charge of a single point charge that is moving along the wire. So let me just write it over here maybe. Q is the charge of a single current carrier.
So why did we write lambda HQ instead of Q? I mean, in the main formula we have QBB. Here,
Yeah.
for example, for perpendicular we have lambda HQBB.
You see, we did write Q, only Q, QUB. This is the force, the parallel component of the force acting on one of the charges. But we have many charges. The total charges we have is lambda times H. Because lambda is the number of current carriers we have per unit length. We have a length of H of them. So lambda H is the total number of current carriers. Each one has a charge Q. So this is the total charge of the current carriers. And we multiplied lambda H by QVB or QUB, where QVB is the force acting on the vertical component of the force acting on a single one. QUB is the horizontal component of the force acting on a single one. But the wire has many of them. So if you want to calculate the total force acting on the wire, not a single charge, I just multiply the force acting on a single charge by the number of charges in the wire. So this is the total.
Yani hem paralelde hem de perpendicular'da yani şey var. Yani manyetik alan var, B var. Fakat hani iş yapmıyor dedik. Burada niye etkisini görüyoruz o zaman manyetik alanın? Yani bu yine hala iş yapmıyor.
You see, there is a force. Not all forces do work. This is just the force.
Ama alta inebilir misiniz? Şurada dV'yi hesaplarken de B var burada.
You see, I'm saying that the battery should do work. Battery is doing work. Battery should be creating this electric field which is pushing the charges along the circuit. So how much force should the battery exert, or the electric field created by the battery exert? It should balance this component. Okay, so there is this magnetic force it has a horizontal component. The battery should be pushing the charges with this magnitude to keep a steady current. So this is the force exerted by the battery. Okay, the force that the battery should exert is related with the magnetic field. Because if there is no magnetic field, there is no horizontal force. So that's why the B appears also here. But this is not the force the magnetic field is acting. It is the force that the battery is exerting, which is related to the magnetic field.
Peki hocam bu kuvveti elektrik alan kullanarak yazamaz mıyız?
Of course you can. What is the magnitude of the electric field?
F bölü Q.
U times P. You see, this is at least the horizontal component of the force acting on a single charge. If you want to balance this with an electric field, this should be equal to Q times E. And the electric field has to be equal to U times P if you want to keep the constant current. So let's just imagine we have a region of space where there's a uniform magnetic field. And we send a charge in this region. So at this instant, what is the direction of the force? Let's say this is an electron. What is the direction of the force? So by just looking at where the trajectory bends, you can tell what is the charge of the object, whether it's a positively charged or a negatively charged object. So if it is positively charged, the force will be upward. If it is negatively charged, the force will be downward. So there is no electric field, there is only magnetic field. So does the magnetic field do any work on this charge? Does the magnetic field do any work on this charge? Does it do any work? It can cause displacement, but it doesn't mean it works. It does any work. Does it do any work? Does the magnetic field do any work?
Hocam şeyde çalışıyoruz. Mesela bir circle, evet, bateri o işi yapıyor diyebiliyoruz ama mesela siz sadece bir tane yük çizdiğiniz zaman hani yani ortada başka bir şey yok. Sonuçta bunu yapan tek şeyin magnetic field olması gerektiğini düşünüyoruz.
Of course, that the magnetic field is rotating the object, but that doesn't mean it is doing the work. Am I doing work now? No. Just like that, magnetic field. Why am I not doing work?
Çünkü
Are you convinced that I'm not doing any work as I'm on this keyboard?
yer çekimini dik olarak hareket ediyor.
Because there is displacement, but the displacement is perpendicular to the force that I'm exerting. That is why I'm not doing any work on the keyboard. In this example, the magnetic field is not doing any work on this charge. Yes, the charge is moving. The velocity of the charge, it didn't acquire due to the magnetic field. You created somehow, but you caused it an acceleration through an electric field. So the charge has an initial velocity. The magnetic force will always be perpendicular to the velocity. The charge will be displaced, but the force will always be perpendicular to the displacement. At the next instant, for example, the charge will rotate so that the velocity will rotate so it's moving, let's say, in this direction. But in that case, the magnetic field will be in this direction, still 90 degrees. If the velocity is in this direction, the force will be in this direction, again 90 degrees. The force will always be perpendicular to the displacement. And hence, it is not doing any work. There is no work done. Okay, now do you remember the work kinetic energy theorem? The total work done on an object is always equal to the change in the kinetic energy of the object. This is always true. If you know all the forces acting on an object, you can calculate the total work done on an object, and this total work done on the object by all the forces acting on it is equal to the change in the kinetic energy. Now, in this problem, at this instant, the only force acting on my charge is the magnetic field. So the work done by the magnetic field is 0. So what is the change in the kinetic energy of this object? 0. Well, I don't know yet what kind of a motion this charged object will do, but I know that whatever the motion is, its kinetic energy will always be the same. But the kinetic energy is nothing but the 1/2 times mass times the speed of the object. Since the kinetic energy doesn't change, the speed of this object will never change during this motion. There is no speed change, only the direction of the velocity will change. Now let's think about the motion that is at constant speed. There is a force acting on the object, but this force is always perpendicular to the velocity. So what kind of motion is this? Uniform circular motion. So the object will carry uniform circular motion. So in uniform circular motion, we should have some centripetal force, which should be equal to mv squared over r. So let's see, this object will go around such a circle. This is the radius. And if an object carries a uniform circular motion, it just means that there is a force towards the center of the motion, and that force should have this magnitude. Now, the only force here is the magnetic force, and the magnetic force should be providing this centripetal force, and we know that the magnetic force is equal to QV times B. So we can cancel the V's. M over Q will be just RB over V. So if you just observe the particle, if you just somehow can see the particle moving in a magnetic field, you can measure the radius of its orbit. You can measure the magnetic field. Well, if you can follow the trajectory, you know the velocity. you know the speed of the object. So everything over here you can determine either because you created or by just looking at how the particle moves as a function of time. So by just measuring these quantities, you can determine what is the mass over the charge ratio of the object. Now let me show you an example of this. Well, if I'm lucky to find it. Oops, just give me some moments. Well, I will not be able to show you.
Hocam şu kabloyu çıkarıp tekrar baksana.
I mean, the wire is quite long, so there's some problem somewhere. I mean, too bad. No. Okay, so now what you will see is no, don't play it. Just look at the picture. This is what you will see. A big circle, a straight segment, and then you have a almost straight path. There is a magnetic field in this region. Now, this is a metal plate. This is the first discovery of a positron, the antiparticle of the electron. Can you see it from there? Okay, you have already seen the picture. You see, this is a metal plate, so the idea is as this, I mean, just by looking at this picture, you don't really know. I mean, you are not really watching a movie. You just see this track. You don't really know whether the charged object moved in this direction or in the other direction. So that is the motivation for putting this metal plate in between these two halves. So the idea is if you have a charged object, and if it passes through this metal plate, it will lose some of its energy. And what is the radius for slower particles? Is it larger or smaller? You already have the expression for the radius. So if an object is slower, is the radius larger or smaller? If the particle is slower, then the radius is slower. Well, the radius of curvature over here is smaller than the radius of curvature over here. So this basically tells us that whatever the particle is, it entered from here, crossed this metal plate, and it had less energy in this segment. Well, you already know the direction of the magnetic field. That is, in this setup, the magnetic field was into the screen. And the object is moving in this direction or in this direction. Well, the force acting on this one should be in this direction, so because it is bending in that direction. This is the direction of V cross B. So this basically tells us that the charge of this object is positive. By just measuring this curvature, this curvature, they already knew more or less what the energy of this particle was. So they know the energy, and they know energy, so they know the velocity. They know B. They can measure the radius. They know R. So that means they can measure the Q over the mass ratio. And it just turned out that the Q over the mass ratio of this particle is exactly equal to the electron, but with opposite charge. So that was the discovery of the positron.
Hocam onu nasıl çıkmışlar?
Well, what they do is they capture pictures frequently. Of course, it's not, the time resolution is not great. Sorry, they don't take pictures. What they do is they just use photographic films. How many of you have seen a photographic film? Okay, you are astrophysicist. Okay. Do you know what a photographic film is? Now it's always the digital cameras, but in the old days we didn't have digital cameras. So there were basically films sensitive to energy deposition. So they were sensitive to light. So when light falls on this film, there are chemicals that are sensitive to the light. So their chemical properties change. And you can process these films later on and create images. I'm sure you have seen in some films, they go into a dark room or a room with red lights. So that is where they develop the films. And you can have photographs. This is one of them. So basically, they put the films there. So they don't really know when the particle went through. But basically, they just take the picture.
Güzel hocam.
Do you want the movie? Oh, yes. So this is the picture we have. So you see, the curvature is, the radius is larger here, smaller over there. So that way we can tell that it is moving in that direction. Now, of course, this is assuming that the velocity of the particle was perpendicular to the magnetic field. Well, that is not necessarily the case. I mean, you have, let's say, magnetic fields in this direction. The velocity need not be perpendicular. It might make some angle different than 90 degrees. It might have a component along the direction of the magnetic field. But you see, the V cross B is always perpendicular to B. This is always perpendicular to B. So there is no acceleration in the direction of B or in the opposite direction of B. So if you have a charged object, let's say you have a region which has a uniform magnetic field, a charged object enters in this region, not perpendicular to the magnetic field, but with an angle. In the perpendicular plane, it will still do this circular motion. But in the vertical plane, it will just do motion with constant velocity. So it will basically do this helix. This will be the motion of my particle when it enters the magnetic field. Well, Earth is a magnet, a huge one. Where is the magnetic north pole of Earth? Yes. The magnetic north pole is in the geographic south pole, close to the geographic south pole, let's say. Because the south pole is attracting the south pole of any magnet we put. So the north pole attracts the south pole. So these are the magnetic field lines, more or less. Yep, so this is Earth. Now let's imagine sun is, I'm sure you have heard of solar winds. Solar winds are nothing but, most of them at least, are charged particles, protons and electrons. So one of them enters our zone, comes close to the Earth. Well, you see, it is not perpendicular to the magnetic field. It is horizontal to it. It has a perpendicular component and also a horizontal component. So it will basically rotate around the magnetic field lines as it moves. But you see, as it comes towards the North Pole, the magnetic field lines start to change fast. So this is not a uniform magnetic field. So in this region, the magnetic field lines kind of come to converge to a point. In such regions, the moving charged objects will basically feel a force away from it. So it started here. It started circling around the magnetic field lines. When it reaches the poles, it will feel a force in the opposite direction. So it will just go back and forth between the North and the South Pole. So in a sense, these solar winds, at least most of them, cannot really reach Earth. At least not the regions that is habitated. Well, it is trapped over there. I think they were called Van Allen belts, right? Yeah. It's highly radioactive. You have all these charged particles, high energy charged particles, trapped there. But we see their effects. You see, what this phenomena will do is all these charged particles go to the poles. If they hit over here, they go to the geographical South Pole. If they hit above, they will go to the geographic North Pole, and they will just go back and forth. So what is special about the geographic North and South Poles? That you know some nice phenomena, some artistic phenomena. Northern Lights is caused by this one. So basically you have all these charged particles coming quite close to the Earth on the poles. Well, they are colliding with the atoms in the atmosphere, mainly the oxygen and the nitrogen. But the oxygen and nitrogen will be excited due to these collisions. And then they will be excited, and then they will lose energy, emitting light. And so you get the northern lights. Well, you see, they do approach Earth in these regions, which is close to the atmosphere. Now, this is a nice phenomenon. You can trap charged objects. We are also trying to use exactly the same phenomena in nuclear fusion research. Well, fusion, I think it's a single S. Well, that is what we are using in nuclear reactors and nuclear bombs. You just break up the nuclei. Fusion, you try to combine the nuclei. That's basically what's happening in the sun. So in the sun, under huge pressure, the nuclei are very close to each other, at least at the center. But if they are the problem is there is the electromagnetic repulsion. The nuclei are all positively charged, so you cannot just put the nuclei together. They don't want to come together. So you have to heat them up. Now what happens when you heat them up is they're already packed, and when the temperature goes very high, they will be moving fast, and during these very fast motion, they will just overcome this electromagnetic repulsion. They can come very, very close. So close that the nuclear forces start to be more important than electromagnetic forces, electrostatic repulsion. If they can come so close, then they will just combine. They will fuse together, releasing energy. So that is where the energy of the sun comes from. But in the sun, you don't need to worry about burning anything, so you just burn everything. But on Earth, we have to kind of hold this material in a compact region. We have to create some pressure and also heat. But that much heat, we don't have any material that can stand the heat, that high heat. I mean, as far as I know, all the materials melt, let's say, at 3,000, 4,000 Celsius. So, but these things should go even higher. So how do you hold them? How do you hold them in a given place? This is the answer. you create what are called magnetic bottles. You create a magnetic fields such that they all start from a given from a very small region. You try to form such bottles. Well, since the magnetic field lines are converging very fast, when they approach these endpoints, they will be pushed back and forth. So they will just go back and forth in between. Well, there's still the problem of leaks, though. I mean, if you have a charged object that has a large vertical velocity, it will be pushed back. But you see, these particles are also colliding with themselves. So from time to time, you will end up having a particle that is moving horizontally. There is nothing practically that's able to stop that. So it will just go out. So that's one of the problems. Another problem that the fusion researchers are facing is that, okay, you create this magnetic field, you put wires, and you can determine the shape of the wires, etc. So you can fix the shape of the magnetic field that you create. But in here, you put charged objects, and these charged objects are constantly moving around. So there's a current there. Well, there is a magnetic field that you created, but there is this additional magnetic field created by the moving charges there. So it modifies the magnetic field that you create. So how do you keep this system stable? That's one of the most difficult tasks that they are facing. They couldn't yet resolve it. There are many instabilities where this bottle basically breaks down. But research is still going on. Yes, any question before you go for a break? Okay, see you after 10 minutes.